The next elementary signal is ramp function. So first we'll see what is a continuous time ramp function. The continuous time ramp function starts at t is equals to 0 and increases linearly with time. Linearly with time. That means as time increases, the ramp function also increases. Right? It is defined as r of t. This is defined as r of t. R of t. It is 0 for t less than 0. 0 for t less than 0. And for t greater than or equal to 0, it is defined as a into t. A is some constant and it is multiplied with t. For all values of t greater than or equal to 0, r of t is equal to a into t, and for all values of t less than 0, r of t is equal to 0. Now, if this a is equals to 1, we call this ramp function as unit ramp function. We call this ramp function as unit ramp function, right? That means at t is equal to 1, the amplitude will be 1. At t is equal to 2, the amplitude will be 2, and so on, right? That is unit ramp function. Now similarly, we'll see the discrete time unit ramp signal. Discrete time unit ramp signal. So the continuous time unit ramp signal r of t, how is it defined? It is defined as 0 for t less than 0, t for t greater than or equal to 0. So when you come to the discrete time unit ramp signal, we denote it with r of n. It is 0 for n less than 0 and n for n greater than or equal to 0. Now we can draw the mathematical representation like this. For n, this is n and this is r of n, right? For 0 and values less than 0, it is 0. For 1, the value is 1. For 2, the value is 2. For 3, the value is 3, and so on, right? This is 1, this is 2, this is 3, and so on. It goes up to infinity. Right? The same thing, we can show it here, right? It goes up to infinity. Now this is the relation between continuous step impulse and ramp. If you look at the ramp function r of t, it is defined as 0 for t less than 0, t for t greater than or equal to 0. Now, if you differentiate this with respect to t, d by dt of r of t, what will we get? We will get 0. Differentiation of 0 is 0 for t less than 0, and differentiation of t with respect to t is 1 for t greater than or equal to 0. Now what is this function? This is same as unit step function u of t. So when you differentiate r of t, we get u of t, and when you differentiate unit step function, we get del of t. We have already seen this proof. How is it done? Now the reverse operation of this, when you integrate del of t, we get u of t, and when you integrate u of t, we get r of right? Now the next elementary signal is sinusoidal signals. So general expression for any sinusoidal signal is x of t is equal to a cos omega naught t plus phi. This is the phase angle, this is the fundamental frequency, and a is the amplitude of the sinusoidal signal, right? So there are two types of sinusoidal signals. One is sine and the other one is cos. So sine looks like this, right? Cos looks like this, right? The same thing we'll show in the next slide. Cos omega t, at 0 it has a maximum amplitude and then gradually decreases. At pi by 2 we have 0, at pi by 2 we have 0, and it is -1 at pi, right? At pi it is -1. This is omega t, right? For sine, 0 at omega t equals to 0, 1 at omega t equals to pi by 2, again 0 at omega t equals to pi, -1 at omega t equals to 3 pi by 2, and again 0 at 2 pi. This is sine. Now the period of this cos and sine, if you look at it, it starts at 0, there is 1. Again, when you get one amplitude at 2 pi, at 2 pi we get amplitude 1. So this portion of the signal keeps repeating again and again, right? The same thing keeps repeating. So the period is 2 pi. Similarly here, this is one portion of the signal which repeats over time, right? Again here also the period is 2 pi. Now we have already seen the continuous time. Now it is discrete time sinusoidal signal. In place of t we just have n, that is the general form. Now here if you look at this signal, what is the period of this signal? We have to find the period of this signal. So this is the portion of the signal that keeps repeating itself, right? So from this point, so this is the first sample, second sample, third sample, fourth sample, fifth, sixth, 7, 8, 9, 10, 11, and 12. Again we are getting the first sample, so we will not count this. So there are 12 different samples that keep repeating again and again. The same thing is repeating again. So the period of this signal is 12, right? The period of this signal is 12. Now we have finished the sinusoidal signals. The next one is exponential signals. First we'll look at continuous time exponential signals. The general form of exponential signal is c into e power at. C is C and C, both C and A are generally complex. Now, if we look at real exponential signals based on C and A, if you look at real exponential signals, both C and A are real values, right? C is just a number, A is also just a number. Based on how this value of A changes, we'll have two different exponential signals. A can take a value greater than 0, or A can take a value less than 0, right? When A is greater than 0, e power some positive value, right? E power some positive value. So it keeps on increasing. The exponential signal increases. At A equal to 0, we have the amplitude of C into e power 0, that is C. This is not A, it is C. When A is less than 0, e power minus at it becomes. So e power minus at is nothing but a decaying exponential. Decaying exponential. As time increases, the exponential decreases. Here, as time increases, the exponential increases. A greater than 0, we get a growing exponential. A less than 0, we get a decaying exponential. And here it is a double exponential or double-sided exponential. So basically what we are doing, we have one rising exponential and one decaying exponential like this. This is the rising exponential. This is the decaying exponential. So we'll just take the left half of the rising exponential, and right half of the rising exponential. How does it look? It looks something like this. Left half of the rising exponential, right half of the decaying exponential. That is this. Right? What is the formula for rising exponential? E power minus at. Right? E power minus at. Sorry, rising exponential is e power plus at. And we only want the left half. We do not want the values of t greater than or equal to 0. That means we should multiply it with u of minus t, right? If you multiply with u of t, you get only the right half. If you want only the left half, we multiply it u of minus t. Similarly, here, the decaying exponential, it is e power minus at. We only want the right half, so we multiply it with u of t. You add these two signals, we get one form of the double exponential signal, right? One form of the double exponential signal, right? Now, the other form of double exponential signal is we will consider right half of the rising exponential and left half of decaying exponential, right? Right half of rising exponential, what is it? E power at. We want only the right half, so multiply with u of t plus left half of decaying exponential. Decaying exponential is e power minus at, and we only want the left half, so into u power minus t. U power minus t. If you look at the graphical representation, the right half of rising exponential and the left half of decaying exponential, right? This is t and this is your double exponential signal. That's how we get these graphical representations and mathematical representations. So this signal here can be simplified into e power a mod t, right? That means mod t, if you want to substitute values of mod t means how can we write it as? We can write it as mod t is equals to plus t for t greater than 0 and minus t for t less than 0, right? Minus t for t less than 0. If you substitute it for t greater than 0 means for u of t greater than 0 means u of t, it is just plus t. So in place of mod t, we'll just write t. For t less than 0, that is u of minus t, in place of mod t, we write minus t. So e power minus at, right? So this is the one form of double exponential and the other form of double exponential. Then the general complex exponential signals. This is the general expression for complex exponential signals. C into e power at. That is the same thing as what we saw as C into e power at. Right? Previously we have considered C and A to be real numbers or real values. Now we will consider C and A as complex values. So the complex value, we can write it in polar form and rectangular form, right? Let us take C in polar form. Polar form means I will write this C in terms of its magnitude and phase. Magnitude is mod C and phase is e power j theta. And similarly, A is also a complex number. I am going to represent it in rectangular form as r plus j omega naught. Now I'll substitute these uh, complex numbers of C and C and A in the original expression of or general expression of C into e power at. So after I substitute, I'll simplify. So mod C e power rt. So e power rt into e power j, I'll take common, theta plus omega naught t. Theta plus omega naught t. Right? Now this e power j theta, this whole thing, I can write it as cos theta plus j sine theta, right? I can write it as this form. So I will now expand this in terms of cos and sine. So mod c e power rt into cos omega naught t plus theta plus j mod c e power rt into sine omega naught t plus theta. Now depending on value of r, this signal varies. How will it vary? What will happen if r is equals to 0? If r equals to 0, this becomes 1 and this becomes 1. What are we left with? We are left with cos and sine. So the real part will be a cos signal and the imaginary part will be a sine signal, right? It looks something like this. The real part will be a cos signal and the imaginary part will be a sine signal, right? Something like that. Now, if r is greater than 0, r is greater than 0, what is this part? E power rt. E power rt is a growing exponential. So the real part will be a cos signal multiplied with growing exponential. This is a growing exponential, right? These dotted lines represent growing exponentials. Okay, these dotted lines represent growing exponentials. So the cos signal when multiplied with the growing exponential will look like this. It will just modify the amplitude of the cos signal, and the sine signal is also a growing exponential. So the sine signal will be, just draw the cos and sine signals of a growing exponential. So for a growing exponential, it will be something like this. So this will be my growing exponential, and my cos signal will look like this. My cos signal will look like this. And my sine signal will look like something like this. This will be my sine signal, right? Let me draw it with a different color. I'll draw it with a different color now. This will be my sine signal. That is for r greater than 0. Now what will happen if r is less than 0? If r is less than 0, this is a decaying exponential. It is a decaying exponential. So let me take a decaying exponential on both sides. Right? Now my real part is a decaying exponential multiplied with a cos signal. Real part is decaying exponential multiplied with a cos signal. And the imaginary part is decaying exponential multiplied with a sine signal. Right? So it's multiplied with a sine signal.